back, and Zhenchang Liu will present the paper.
Thanks for the introduction. And my name is Zhongxin Liu from Zhejiang University. I'm very glad to be here today to present our work named CCRep Learning Code Change Representations via Pre-trained Code Model and Query Back. The background of this work is that during software development, developers constantly perform code changes to implement new features, to fixing bugs, and to do refactorings. It is very important for many software engineering tasks to understand and analyze the code changes they used. For example, for the commit message generation task, it is necessary for us to summarize the content and intent of the code changes. We refer to these tasks as code change related tasks. To automate these tasks, a popular and effective paradigm is that we can first use a deep learning model to convert or to encode the input code change into feature vectors. And then we can simply input the feature vectors into the downstream task-specific modules such as predictors, classifiers, generators to perform and complete diverse code change-related tasks. We can refer to these feature vectors as code change representations and refer to the deep learning model as code change representation model. So we can see that it is intuitive that the quality of code change representations is critical to the performance of the code change related tasks because they are the basis of the downstream tasks. So an important question is, how can we learn good code change representations for diverse downstream tasks? To answer this question, let's first check out a simple example. We can see that in this example, there is a code change, and this is the lower point is its commit message. And we can know that this commit just simply move line 5 to line 7 and to prevent the edit post activity error. If it is error, then if it is error, we can recover the edit post activity. From this example, we can have several observations. And the first observation is that the changed code is the core of the code change, which is very intuitive. For this example, if we check the changed code part, which is line 5 and line 7, we can see that line 5 is just creating the post ID, and the core of the code change is move post ID creation. By comparing line 5 and line 7, we can see that they are equal. So this is a move operation. So from the changed code, we can know the core of this code change, which motivates us that when representing code changes, we should explicitly identify and highlight the changed code. And another observation we observe from this example is that the context may provide important information, which is also somehow intuitive. Because for example, in this example, we can see that if we only focus on the changed lines, line 5 and line 7, we cannot know that this post ID creation is moved to the try-catch block, and we cannot infer the intent of this commit message, which is to recover from errors. But that's not enough, because we can see not all the context is useful. For example, line 2, line 4, line 8, and line 10 is unrelated to the content and the intent of this code change. So from these observations, we can see that when representing code changes, we should adaptively capture important information from the whole code change instead of only from the changed part, and we should do adaptive capture instead of regard all the context equally. So based on these ideas, we propose a novel approach named the CCRep. CCRep, this is its framework. We can regard CCRep as a general code change encoder. It first uses diff tools to align the before change and the after change code snippets, so we can identify the changed code fragments either at the line level or at the token level. And we will store this alignment information for further stages. And then we will use a pre-trained code model to obtain the contextual token embeddings of the before and the after change code, respectively. These token embeddings encode the contextual information in the code change, and they form the basis of knurling good code change representations. And it is worth mentioning that the generalizability of the pre-trained code model also contributes to the generalizability of CCRep. And finally, we propose and use a novel mechanism named queryback. Queryback will highlight the changed code fragments, and it can adaptively select important information by explicitly interacting the changed code part with the whole code change. So how can the queryback mechanism do this? This figure presents the overall framework of the queryback mechanism. Considering that different downstream tasks may focus on the information of different granularity, for example, the token level or the line level, so we propose 3 variants of the queryback mechanism: token level, line level, and hybrid queryback. Due to the time of the limitation, of time, I'll just introduce the token level queryback. In the token level queryback, we will take as input the contextual token embeddings and the alignment information proposed and extracted by the former phases. And then we will explicitly identify which tokens or which lines have been changed and selected their contextual token embeddings. Then we will highlight the changed code by building a change-aware query, QT or QL, from the selected contextual embeddings. And we will expect that such query or such feature vector can encode the information in the changed part. And then we will consider the feature vector as a query, and we will consider the token embeddings of the whole code change as the keys and values, so we can use a multi-head attention mechanism to adaptively select important information from the keys and values based on the query. Okay, to evaluate the effectiveness of CCRep, we have used 3 downstream tasks. The first is we use automated patch correctness assessment task, which the input of which is a plausible patch that is generated by an APR, an automated program repair tool. And our goal is to classify whether it is correct or not. And the second task is just-in-time defect prediction task. We will predict whether the input commit is defective or not. And the third one is the commit message generation task. The goal of this task is to generate a concise summary to summarize or describe the content and the intent of the given commit. The first 2 are classification tasks, and the last one is a generation task. And we have evaluated CCRep on the CMG tasks on 2 data sets, and these 2 tables present our results. We can see that on the two data sets, our approach outperforms all the baselines by significant margins. We have done statistical tests. And then on the APCA, the automated patch correctness assessment task, and the JITDP task, we also outperforms the baselines by substantial margins. So these results show that CCRep can effectively boost diverse code change related tasks. So in summary, in this work, we have pointed out that when representing code changes, we should not only focus on the changed part, but also the context, and we should adaptively capture important information from the whole code change. And then we proposed a novel queryback mechanism and construct a novel approach named the CCRep to be a general code change encoder, which can be used in diverse code change tasks and can boost existing approaches. And we have uploaded our replication package to GitHub, and you're welcome to check out. So that's all. Thank you.
Time for questions. If you have questions, please come up to the microphone. maybe I didn't get it. So you have a very nice motivation. They said that the code change, and you move from line 5 to line 7, but the information in the commit message is more important. And I probably lose the connection that in the query back, is that the query back method is about finding the most important keywords in the commit message so that you can basically build an embedding so that it represents the change better? Or it's, in my way of thinking, is basically you trying to use some of the point network to identify which the location of the keywords is more important so that you can, let's say, weighted average of these embeddings into a more useful embedding.
I'd say it's the second way. So our goal is to nerd this model with the downstream task, with the data of the downstream task. So we can use this label data to nerd which part of the changed code we should focus, and use the changed part to query back to retrieve important information from the whole code change. So our starting point is the changed part, and based on the downstream task we use, we should know which part of the changed part we should focus, and we use this implicit information to retrieve the whole code change, so we can know what information in the whole code change is more related to the changed part that we care.
Hi, thanks for the talk. So could you give more details on why you use a pre-trained model and how you fine-tune these models? Or have you tried to fine-tune your model without pre-training?
Actually, we did not. We do perform the experiments without pre-training, and we do experiment with different kinds of pre-trained model. For example, in this work we use CodeBird, and we also tried the Robota, but we find that CodeBird can provide its own benefits because it is pre-trained on code. And the reason we use pre-trained model is that we only have several downstream task data. So the data of downstream tasks are less than the pre-trained data. But we need to, if we do not use pre-trained model, we need to train the whole model including the token embedding and the query back mechanism, which is very difficult. But if we use the pre-trained model, we can focus on training the query back mechanism. And the pre-trained model already provide a good basis for us to nerd the code change representation. Okay. So, and it is more general if we use the pre-trained model.
Okay, so have you tried to, for example, train your model without the pre-training?
Yes, but it cannot beat this model with pre-training as the reason. The reason is I just discussed.
Okay, thank you.
Thanks for your presentation. I have a question. Do you think the larger pre-trained model can solve the problem mentioned by your motivation, such as the ChatGPT or Codex? Can these large pre-trained models can learn about and understand the intentions of the code changes directly?
Yeah, I think for some specific downstream tasks, maybe a large language model will perform better. But this work is done last year. At that time, we cannot use large language model. And this is the first point. The second point is that this paradigm or this model is much more cheap than the large language model, and we can see. And we did, and another choice is that we can indeed pre-train a code change model. Yeah, that we can use code change data to pre-train a model. And actually, we have done this in this year's FSE. So at that time, we do not have so many GPUs, and we do not have so many money to pre-train a code change model from the scratch. So we change our mind and say whether we can use existing and cheap code model to build a better code change representation model. And this is this work's goal. And we say And this work is independent from the pre-trained code model. If there are more advanced pre-trained code model, we can simply replace the middle part of this model, and the queryback mechanism can also work.
Okay, thank you.
All right, thank you very much. Let's thank the speaker. I would like to ask the third speaker to come up to the podium. All right, our third paper presentation is also a research paper, and it will be presented by Cheng Gao.
Okay, thank you. Hello everyone, my name is Shuzheng Gao, and I'm a second-year master student from Harbin Institute of Technology, Shenzhen. I'm glad to be here to introduce our paper, keeping pace with ever-increasing data towards continual learning of code intelligence models. Recently, code intelligence has drawn more and more attention and has been used to help developers in various applications, such as code summarization and vulnerability detection. However, these models are always trained on a pre-collected and fixed dataset in an offline manner. This makes them cannot acquire up-to-date knowledge in the emergent data. In the real world, the data are always produced in an ever-increasing fashion. For example, the number of GitHub repositories and the JDK APIs increased substantially in recent years. These new repositories and APIs may contain various programming knowledge that are crucial for providing up-to-date and high-quality assistance for developers. Therefore, how to enable code intelligence models to continually learn from ever-increasing data is of vital importance. But dealing with this problem is not easy. One straightforward solution might be directly fine-tuning the model on new datasets. But this method suffers from the catastrophic forgetting problem. As shown in these two figures, directly fine-tuning the model on new datasets leads to obvious performance degradation on the first dataset. And another straightforward solution might be retraining the model on all historical datasets. But these methods will lead to severe computation overhead and is always infeasible in practice. Therefore, in this paper, to deal with this problem, we propose to resort to continual learning. Continual learning is a popular research field in AI that aims at learning without forgetting. And we mainly focus on the replay-based and regularization-based methods in continual learning. The replay-based method deals with the forgetting problem by retraining the model with a limited set of examples stored from previous datasets. And the regularization-based methods like EWC add weighted regularization to the L2 distance of the parameters in the last model and the current model. Then I will introduce our method repeat. Repeat combines the replay-based methods and regularization-based methods and improve them based on the characteristics of code intelligence tasks. In the replay-based part, instead of random example selection in EMR, we take the existence of code patterns and noisy data into consideration and propose to select representative examples that are both diverse and informative. And in the regularization-based part, considering the popularity of code reuse, we propose to change the fixed weight lambda in EWC into an adaptive term based on the similarity of different datasets. And then I will introduce these two parts in detail. after the training stage, we select the examples as follows. First, to reduce the redundancy of code patterns and functionalities in the selected examples, we propose to improve its diversity by first dividing the whole datasets into key clusters, and then selecting examples from each cluster. And then, considering the existence of noisy samples, we propose to select samples with lowest training loss in each cluster to filter those possible noisy data. And at last, to maintain a fixed size of examples, we also need to reduce the preserved data in previous datasets. So here for each previous dataset, we remove the samples with the highest training loss we have calculated before. So based on the both process, we can get the exemplar set, and it will be used to retrain the model on the following datasets. And in the adaptive parameter regularization part, considering the popularity of code reuse in the process of software development, there might exist some similar code snippets in different datasets. And here we assume that if two datasets are very similar, a strong regularization on the parameter should be applied and vice versa. So therefore, we propose to first measure the similarity of current dataset and the saved examples by TF-IDF and cosine similarity, and then use it to substitute the original fixed hyperparameter lambda in EWC. And we evaluate our method repeat on 3 code intelligence tasks, including code summarization, vulnerability detection, and code clone detection. The first task is a generation task, and the other two are classification tasks. For the data size to simulate the continuous learning scenario, we build upon existing data sets that contain project information and construct a project-level continuous learning version for them. Specifically, we randomly split the whole data sets by the project into 5 parts and treat each part as a new individual data set. And the statistics of the data is shown in this table. For the baseline models, we experiment with 2 pre-trained code models, CodeBERT and CodeT5, as our base model, and compare repeat with 4 training strategies. Here, FT means directly fine-tuning the model on new datasets. EMR and EWC are 2 representative replay-based and regularization-based methods, and we have introduced them both. And the last method is upper. It uses all historical datasets to retrain the model and is always infeasible in practice. So we only use it as at the upper bound in this experiment. And for the evaluation metrics, to evaluate the performance of each method under continual learning setting, we evaluate them by their average performance on all test sets. So, for example, after we train the model on 5 sequential data sets, we can obtain 5 models. And each row represents the performance of each model on the data sets it has seen before. So here we first calculate the average performance of each model on the dataset it has seen before, and then use the average performance of the 5 models as the final result. So in first research question, we evaluate the performance of repeat on 2 models and 3 tasks. And these 3 tables show the results of code summarization, vulnerability detection, and code clone detection. And from this, we can find that the fine-tuning method severely suffered from the catastrophic forgetting problem. And our method repeat can effectively mitigate it and achieve the best performance on all three tasks consistently. In RQ2, we study whether our method is also beneficial to the generalization on unseen dataset. So here we train the model on the first 4 datasets and evaluate the performance on the 5th dataset. From this, we can also find that our method is, we can find that continuous learning is beneficial to the generalization on unseen projects, and our method can achieve the best overall performance. And then in the application study, we evaluate the contribution of each part of our method. And we can find that all components in our method are beneficial to the performance. And at last, in the parameter analysis, we studied the impact of 4 parameters on the performance, including 2 hyperparameters in repeat and 2 parameters of continuous learning setting. And here we can find that the parameters used in our paper can achieve the best overall performance, and repeat can outperform EMR and EWC in different continuous learning settings. So to summarize, we can achieve the following conclusions for our paper. First, how to enable the code intelligence model to keep pace with ever-increasing data is an important and interesting problem. So in this paper, we are the first to investigate this problem and propose the repeat method. And last, we release our code and data in this GitHub repository. So that's my presentation. Thanks for listening.
Thank you.
So I have several questions. So first of all, when you say select the samples, you try to do in the k-means, which is a numerical value of embedding of the code. And you talk about using the code BERT and the code T5, which I'm assuming that you are extracting the embedding from the CS token. This one is, because code T5 and the code BERT is, depending on the pre-training task, the CRS token might or might not be the best representation of the embedding of the code itself. I was assuming that, I was expecting you were using some auto-encoder styles that reconstruct the code so that you get a better embedding, but you probably have your reasons. The second part is when you do this, you're thinking about you have do the k-means, which on the order of the millions, maybe even the billions of the samples, and you select for this kind of, for each, as diversified as possible as your means, yes? So there will be a computational cost to that because you have to select samples for each category, and there's some details you probably can explain a little bit better. The second part is because you are using 2 mechanisms. One is about this kind of selecting samples. One is about augmented weighting in the regularization. I'm assuming you do this simultaneously. So is that any kind of study or your intuition about when these 2 combine together, will it introducing any instability of kind of a positive feedback effect so that it kind of it doesn't converge or kind of sometimes collapse, something?
Okay, so for the first question, in fact, we conduct the, when we conduct k-means, we get the representation by, in fact, here we use TF-IDF to get the embedding of each code and then apply the k-means. Yes, and it might be the best method, and I think your suggestion is also very good, and we will explore more embedding methods, and Oh, I'm sorry, I forgot another question.
Because you're using two mechanisms together, is there any kind of instability when you do this simultaneously?
All right, I think we're going to take that question offline. Next question.
Yeah, thanks for the presentation. My question is, have you checked for the different data sets if some are out of distribution? So because for the continual learning, we have more problems, generalization problems, when we have out of distribution data sets, if you learn from data sets that are really different. Whereas in your experiment, we don't see if there is a distinction between these data sets. Have you studied the distribution of the data sets and the impact on the results?
We split the data sets by the information. So I think the distribution of data sets are also different, but we don't measure the difference of the distribution in quantitatively. Yes.
All right, unfortunately, we have more questions, but we don't have time, so we need to take those questions offline. Let's thank the speaker again. The next paper is going to be a tool demo paper, and this is going to be presented remotely. The title of the paper is PCR-Chain Partial Code Reuse Assisted by Hierarchical Chaining of Prompts on Frozen Copilot. And Zhenchang will present it.
Can you hear me? And can you see my slides? Hi everyone, my name is Jiahui, a graduate student from Jiangxi Normal University in China. Today, the paper I'm going to present is called PCR-Chain, Partial Code Reuse Assisted by Hierarchical Chain of Prompts on Frozen Copilot. Okay, first I will introduce the issue in the paper. Partial code from API documentation and Q analysis is frequently reused in programming tasks, but may not compile due to non-fully qualified names and last-mile syntax errors, such as unbalanced parentheses and missing commas. As shown in the left figure is a Java code snippet that contains non-equivalence and last-mile syntax errors. Line 6 contains non-equivalent for string user class, while line 4 has a last-mile syntax error with an incorrect symbol in the loop. When the developers copy this partial code into the IDE, it will result in compilation errors. Simple cannot be resolved and unexpected token. Due to these errors, partial code can only used to be as test, which limits its use in code search, code vulnerability analysis, program techniques, and so on. To infer equivalence for non-equivalent type in partial code, some makes type inference based on abstract syntax tree, and some fix syntax error based on programmer's analysis. But there are some challenges out of vocabulary, large amount of data, and time-consuming. Our approach based on large language model like Copilot, which have extensive code knowledge to solve out of vocabulary program. We also utilize an in-context learning approach that allows model to learn from a few examples of specific downstream tasks in context and complete them by mimicking those examples. This eliminates the need for special model training and deployment. Then, we design an underlying approach to assist the implementation of PCR-Chain, which involve prompt architecture and prompt design. The prompt architecture is framed by 3 design ideas: hierarchical task breakdown, prompt composition, and mix of prompt-based AI and non-AI units. This design is based on function analysis. According to different function or different performance of the same function in a given range, the task can be divided from top to bottom into more fine-grained subtasks, or even a series of executable atomic units. Based on the previous layer task is refined in next layer task. Based on this design, PCR-Chain has a 3-layer architecture. As shown in the layer 1, the root module is partial code reuse that resolves equivalence of simple names and fix last-mile syntax errors in the partial code, so that uncompilable partial code becomes compilable code. As shown in the layer 2, the root module is divided into 2 submodules because it performs 2 distinct functions successfully. One submodule is FQN inference. It resolves non-FQNs in partial code. Another is syntax error fix. It checks and fixes last mile syntax error in the code. As shown in the layer 3, the functional units are classified into two categories: AI units that utilize fuzzy reasoning based on large language model, and non-AI units that follows predefined rules or logic. The first submodule is further divided into three units. Same name extraction units extract the simple name of non-FQNs in partial code. Simple name to FQN units convert simple name to FQNs, and FQN supplement units as import statement with FQNs at the start of the partial code. The second module is further subdivided into two units. Code check unit determines whether or not the code contains syntax error, and the code fix unit fixes the syntax error. In this experiment, we randomly selected 50 uncompilable code snippets from Stack Overflow by Huang et al. The accuracy metric is used to evaluate PCR-Chain. The high accuracy of units demonstrates the effectiveness of prompt design, establish a strong foundation for high-quality modules. The successful inclusion of modules highlights the value of prompt composition in connecting units and achieving super outcomes for higher-level tasks. PCR-Chain effectively breaks down text into hierarchical units and modules, effectively blending AI and non-AI units. It also resolves non-FQs and fixes syntax errors, providing further validation of its unity. In conclusion, we propose a new architecture that combines three global ideas: hierarchical task breakdown, prompt composition, and a mix of prompt-based AI and non-AI units. Other than a simple AI chain, we have designed a system at the local level for generating task-appropriate prompts that use in-context learning to resolve FQNs and fix syntax error in partial code. Our method eliminates the need for special model training and deployment compared to supervised fine-tuning approach. The successful completion of units module and the PCR-Chain demonstrates the effectiveness of prompt design, composition, and architecture in resolving FQNs and fix last-mile syntax errors. That's all. Thank you.
All right. Thank you. Any super quick clarification questions? We're moving to fairly short presentations. Each presentation will have only 7 minutes, including questions. So we're going to move to the next presentation. Thank you.
Okay, thank you.
Thanks again. The next paper is going to be journal first paper. And the title of the paper is Towards Learning Generalizable Code Embeddings Using Task-Agnostic Graphical Neural Networks. And Zhang from Concordia University will present the paper. Thank you.
Okay, thanks. So, hello everyone. Today I'm going to talk about our journal first paper, Towards Learning Generalizable Code Embeddings Using the Graph Neural Networks. So code embeddings, before I start the presentation, I want to give you some background about the code embeddings. So code embeddings aim to project the code tokens into a low-dimensional vector space. So for example, we have source code, and we extract code tokens in the source code. Then we use some models like some neural networks models. Then we use these models to train the code into a code embeddings. Code embeddings has been proven to be very useful for a lot of software engineering tasks. And a lot of researchers have proposed a lot of approaches for doing code embeddings. The code embeddings, however, the code embeddings are usually trained and evaluated on the same single task. And they may not generalize very well to other software engineering tasks. For example, in a previous work, they evaluate two code embeddings, code2vec and glove. The code2vec are trained based on the ASTs, and they are trained on the task of method name prediction. In detail, we have the source code, and then we convert the source code into ASTs. Then we use neural network to encode the tree into a vector representation of the source code. For the glove, it are trained on the textual representation of the source code. And they use the code token-to-token co-occurrence statistics to get vector repetition. However, like code is highly structured, and graph representations of code play a central role for many software engineering tasks. And in our previous research work, we show that the structural information in the source code is more task agnostic in training embeddings. Meanwhile, we find that graph neural networks have been proven to be very useful for handling such structural information in graphs. Therefore, we propose our approach, graph code WAG, aiming to learn code embeddings in using graph neural networks with an unsupervised manner. Our goal is to make the embeddings can generalize to different downstream tasks without any fine-tuning. So first, give an overview of our approach. So we have the data preparation and model training. Then finally, we will evaluate the code embeddings. In the data preparation step, the goal is to convert the source code into a graph. So we have the source code, and then we convert the source code into graphs, where the nodes are the tokens in the source code, and the edges are some type of relations between the code tokens. We follow the literature and collect methods from Java GitHub repositories, and each method are converted into abstract syntax trees. Then each AST is represented as a graph, where the nodes are the tokens and the edges are the passes of the AST. So specifically, we have the two tokens, someone and the name, and then we traverse the tree to get the path between any two nodes of the AST. And by it, we also record the result, the other direction of the passes to trying to keep more information of the source code. By iteratively changing the terminal nodes, we can build a graph of the source code. So in the second step, we propose to use the graph neural networks to learn the code embeddings in a task agnostic manner, which means the loss function doesn't depend on any task. So for example, we have the source code, and we have the graph representation, and then we use the code, the nodes surrounding the central node to predict the central node of the graph. In the model evaluation step, we evaluate the embeddings on a total of 6 embeddings. So first, the first research question is to evaluate the effectiveness of our code embeddings. We compare it with several baselines. So as you can see from the box plot, our approach performs comparable or better than all the baselines on all downstream tasks, which means it can generalize well to different tasks. We also can see that our approach produces more stable results across different downstream tasks, different data size. So besides, we show our realization of the embeddings. As you can see, the embeddings always can project the semantically similar tokens into a very close location in the semantic space. So we only show part of the paper. For more information, you can refer to our original paper for more details. Thank you. That's a summary of the presentation. So we present, yes. Okay. Thank you.
Thank you for your presentation. I think the graph neural network might be a better way to process the code. But I missed the process to construct the graph. When will the two nodes will be connected? And what's the training goal of your problem?
So the first question is about how to construct the passes connecting the different nodes, right?
Yes.
So we just traverse the AST tree. The terminals of the AST is the tokens in the source code, and the non-terminal tokens in the AST are the syntactic nodes. So we just traverse the AST tree to find the path connecting any of the two nodes of any of the terminal nodes. So that's the first answer to the question. For the second question, our goal is to for example, we have a central node and we have several nodes connected to the central node. We will use the connected nodes, the nodes that are surrounding the central node, to predict the central node. That's the goal of the task. So we don't rely on any external tasks to train the embeddings.
Oh, yes, thank you. And I have another question. Have you ever tried directly using the
Yes.
AST to and leverage the GN to process the AST?
No. Yeah, but I think we can try that way to train the. Actually, so if we feed all the entire tree to the graph neural networks, there will be a lot of for example, the AST nodes there are only a very limited number of AST nodes. If we just feed the tree into the graph, there will be a lot of duplicate nodes in the graph. So
Yes.
we didn't try that.
Yes.
Our goal is to train the embeddings of the passes as well as the nodes, the tokens in the source code. Okay.
Thank you very much.
Thank you.
There was one more question. We're doing well on time, so we can afford it, I think. Yes, go ahead. One more question.
Actually, it was very similar to the first question. So I guess it has been asked, but I also need more details. I mean, how far to the syntax tree?
Yes. So it depends on the distance between different nodes. If the graph, if the AST tree is very large, then the passes will be very long. In our paper, we try to avoid some nodes that are very far from each other, because we assume that if the distance is too long, the relation will be very weak, which will be noisy for training the token embeddings. Therefore, we just discard such relations.
Do you have a threshold number?
Yes, we have a threshold. And in our paper, we have tried different thresholds to see the effects of the distances.
Yeah, I have a question. You compared with this embeddings
Yes.
techniques, but not with sequence embeddings like code BERT or because in previous work we showed that even if these large language models learn from code sequences, they are able to capture the syntax. Okay, so have you compared your embeddings with those of encoders, sequence encoders, like code BERT or?
No, in our work we didn't compare. What you said is about the contextual embeddings, where the embeddings of the tokens will change depending on the different contexts, right? So in our work we didn't compare with the contextual embedding. We only focus on the non-contextual embeddings. Besides this work, yes.
Okay.
So, but nowadays you know that the contextual embeddings play a very more important roles. Our work is, I guess our work is just want to show that the syntactic information, the structural information in source code is very important for training embeddings. And for example, the BERT or other code BERT can incorporate such information to further improve their approach.
I'm not sure about this claim, so we should talk
Yes, sure,
offline.
sure.
Yeah.
Yes, sure, no problem.
All right. Please go ahead and ask your questions. We still have a couple of minutes.
I wanted to ask a question to the author of the repeat papers. But he's not on the podium.
Yeah, if he's not on the podium.
Yeah. So then I can't ask a question. So I didn't to the mic.
Feel free to ask one more question, and we're going to move on with the next presentation.
So thanks for the presentation. So I have a general question. So in this work, you try to use a graph neural network to learn co-representations. So I'm just curious. So how do you compare this type of, for example, graph neural network-based approaches with sequential-based approaches? For example, some large language models or some pre-trained models on source code.
Okay, so so actually, when for the use of all embeddings, we just every neural network has an embedding layer. We just apply all pre-trained embeddings to the embedding layer to initialize the embedding layer. Then we compare them with other approaches.
Yeah, so basically you represent the source code as a graph, right?
Yes.
And some previous work tries to represent the source code as a sequence.
Yes.
So, for example, have you compared your approach with this, for example?
Yes, sure. We didn't compare with some large language models, but we compare with some like Word2Vec or Glove. They use the sequential information for training the embeddings.
Okay,
actually, when we use the syntax structure information, we are like explicitly to encode the structure, the syntax information of the source code. I guess when given the very limited training data, it will be like perform better to explicitly to give the model the structure information.
Okay, so which research direction is more promising? One is to represent the source code as a graph to learn its representation.
From my view, like if you have very large amount of data, you don't need to care about the information, the inside information of the source code. The model, I guess, will capture such kind of information by themselves. But if you have very limited data, I would suggest to feed the model with any of the information like we can mount from the source code to the model. But the information should also be related to the specific tasks. So I guess different tasks may require different information from the source code.
Hello, I'm Hu Qiang, a PhD student from University of Luxembourg. Today I present our new idea paper, Code S towards code model generation under distribution shift. First, I will briefly introduce some background of what is distribution shift. Distribution shifts where the training distribution differs from the test distribution, which can pose significant challenges for machine learning systems deployed in the wild. Generally, there are two types of distribution shifts. The first one is the synthetic distribution shifts, which means the distribution shifts come from the computer-generated perturbations. For example, here is one example of MNIST C. You can see you add the noise to the original image and can generate the shifted data set. And the second type is natural distribution shift, where the data were recorded in the wild. They are real data, but the distributions are different from the original data. Then the goal of our work is, since there are very limited works that provide the distribution shift data for code tasks, we provide the benchmark datasets, including distribution shift code data, to help evaluate code models. Here is a summarization of our dataset. We can see Code S supports 5 types of distribution shifts, which including task, programmer, timestamp. These 3 types can be seen as natural distribution shift and 2 synthetic distribution shift, token-based and concrete syntax tree-based distribution shifts. These 5 types of distribution shifts, the tails are here. Task distribution shifts, which means the ID dataset and OOD dataset target different tasks. And the programmer distribution shift means the ID data and OOD data target the same task, but come from different programmers. Then the time distribution shift means the ID data and OOD data target the same task, but are written in different time periods. And the token distribution shift means that the ID date and OD date target the same task, but the frequency of tokens that appear in them are different. Finally, the CST distribution shift means that their CST representations are different. This is the dataset details. We provide 3 sub-datasets. The first one, Python 75, was collected by ourselves on the code computation website, and we also modified the 2 existing datasets, Java 215 and Python 800, and generate our distributed shift datasets. Then we have a preliminary evaluation on our dataset. The first task is OOD detection. We can say we evaluate 4 typically OOD detectors, and you can say the average AUC-RC score, they are not good. Some of them are over the 15%, which means the OOD detectors are totally fail to detect the OOD data. So our data provides the first opportunity to provide new OOD detectors for detect the out-of-distribution of code. Then we will evaluate the model generalization ability of code models. We can say in most cases, the model under distribution shift, the performance drops a lot, especially on our synthetic distribution shift, token-based and CST-based distribution shift, which means our dataset provides a lot of opportunity to how to propose a new method to enhance the model generation ability. This is the future plans. We plan to design more types of distributed shift, for example, from the perspective of software domains, and we plan to extend the codeless to support more code tasks, for example, by detection, code summarization, and also we want to build a larger distributed shift based on the industrial perspective, because now the codeless includes the data from the code computation website. We also want to extend it to support the GitHub repositories. And finally, we can investigate the practices to improve the code model generation against OOD using our datasets. In conclusion, we propose code as the first benchmark dataset that provides a fine-grained distribution shift dataset to support the new evaluation paradigm for code models. We perform the evaluation of the effectiveness of existing OOD detectors and the reliability of our distribution defines. Also, we evaluate the code model generation based on our datasets and review the problems of the existing code models. And yes, we provide our dataset online, and we'll come to use it and also contribute to it. Thanks.
All right, thank you. Questions? So you mentioned in your last slide that one of the shift types has the most significant impact on the generalization ability.
Yeah,
right?
yeah.
So which other shift types significantly impact generalizability based on your empirical results?
Yeah, the token-based and tree-based distributed shifts, because they are like a synthetic distributed shifts, we can control the shift degree, and we can attack the model more, more powerful. Yeah. And then compared to lateral distributed shift, it is more harmful, and we need to take care of them.
Do you have any intuition into why you observe this impact?
Yeah. From my view, for example, the program distributed shift, in fact, maybe 2 programs, they have different program behaviors, but they are not very significantly for one task. However, if we use the token distribution shift, we can split the dataset very differently. Then the model fails to predict the OOD data.
right. Okay, let's take one more question. We have time.
Hello. I actually have a question here about the token distribution difference here. So how did you really identify what is in the distribution and what is out of distribution for the token parts?
In fact, we use the density of the tokens. We build the histogram of the tokens and compare the difference between different code and set a threshold to split the data into two parts.
I see. So basically, you have from your token that result. So it's because the token part drops crazy significantly, right? 30% and almost 50% for different tasks. So is this result telling us that okay, so if the tokens that I'm used for the training significantly different from the my testing, so the performance drops a lot.
Yeah. Yes.
Yeah. So this gives me a very interesting insights. It's for most of so have you ever tried for the same task, but from the different data benchmarks? Because what people know most of us doing is okay. So we have a data sets, we split them from 70%, 30% to do the training and testing. And people are trying to reporting that 30% results. So if the same task, but from the different source, so the performance could be crazy bad.
I'm not sure. It might be, but now we only evaluate the same source of data.
Okay, I see.
Thank you very much. Let's thank the speaker again. All right, our final paper presentation and session is also going to be New Ideas in Emerging Results paper. And the title of the paper is Towards Using Few-Shot Prompt Learning for Automating Model Completion. And Miriam Ben Chaden will present the paper.
Thank you. Hello, everyone. I am Mariam. I am a master student at University of Montreal, and I am here today to present the work I did with Lola and Huawei entitled Towards Using Few-Shot Prompt Learning for Automatic Model Completion. So let's start. So domain modeling is important at the design phase independently from development processes to kicking off a project and ensure that it meets its requirements and functions as intended. But domain modeling is a complex task because it needs at the same time knowledge about the domain itself and knowledge about the modeling formalism we want to model in. This is why domain modeling requires assistance, and the goal of this assistance is to obtain a complete and concise models to reduce the time of this task and finally to minimize the cognitive effort. So the idea is to have a model under construction. Here, for example, we have a class diagram as an example of formalism, and we can all tell that this class diagram is not complete and some elements could be added to the model. For example, concepts or class names. So we might use artificial intelligence techniques or natural language processing techniques to get these suggestions. But these ML-based modeling assistants require data. And the problem with data in the domain modeling is that it is always scarce, and also training machine learning models is always challenging. It requires time, efforts, and resources. And finally, we will have to train a machine learning model for each formalism and not only for class diagram formalism. The idea is then to leverage these powerful, the general concepts that are encoded in these powerful large language models. For example, in our work, we use GPT-3, and we want to benefit from the concepts that are encoded, or the general concepts. But the problem is this general concept does not map directly to our model formalism. In our work, we suggest building what we call semantic mapping between what these LLM have already learned and the formalism in which people want to model their work. For example, here the class diagram. So we start by providing the LLM a description. First we work on the prompt. We provide a description, like here we want to generate related concepts. We provide 2 examples or 2 labeled examples, for example, hospital system and reservation system. The idea here, for example, is to whenever we have 2 related concepts, we present them as a couple for the LLM. As I told you, we use GPT-3 as the large language model. And finally, we have to encode the same way our model under construction. At the end, we will have a text. We will have, so to do again a semantic mapping to map back the results obtained and to add them to the initial model. Here we have, I presented, as an example, suggesting concepts or class names within the same formalism or the class diagram formalism. We also studied the attribute suggestions. We only need to work or adapt the prompt and the semantic mapping done. And we also can do this within a different formalism, like a dynamic diagram, which is here activity diagram. And again, we will have to work on the prompt and the semantic mapping. So further details are available in the paper, because I don't have time to share this with you today. At the time of conducting these experiments, the accuracy was promising, so we had good accuracy of suggestions, and we moved to integrate or to build a module to suggest using this paradigm and integrating it into a modeling platform using Series, an Eclipse plugin. And to evaluate all this, we are now conducting a user study to evaluate the usefulness of this method. As key takeaways, I would like to say that LLMs are offering today a paradigm shift in the way we are developing softwares, and prompting and few-shot learning are allowing us to benefit from LLMs without even training or fine-tuning. And finally, semantic mapping is applicable to any modeling formalism and not only class diagrams or activity diagrams. Thank you.
Thank you. Questions, please?
Well, thank you for your interesting talk. I would like to ask about, well, you said that it is like a few-shot learning, so no need for fine-tuning or further training. We know that large language models have the hallucination problem of giving inaccurate or totally wrong results because of the little training, because of maybe little knowledge on the domain. How did you avoid such inaccurate results or totally wrong results that could come out from few-shot learning or not fine-tuning in a detailed way? Thank you so much.
Thank you for your question. It's actually interesting, and we are trying to work on this by conducting this user study to evaluate the usefulness of all this and to see if it's actually giving accurate result. But as I said, we had a preliminary evaluation. It gave good results. For example, let's say 0.7 as accuracy for attribute suggestions. But as I told you, like to evaluate all this, we are now conducting the user study.
In fact, we have to look at this work in the context of domain-specific languages. So we cannot learn or fine-tune for any possible domain-specific language. So the idea here is just to see if we could take what is already learned and how to adapt what the contexts that are captured by these large language models to give them back to any modeling formalism. And we cannot afford to train for every modeling formalism, especially this explains also why we have few model-driven engineering papers in ICSE, because we don't have data in those domains. So compared to code, where we have this huge amount of data. So modeling, we have few data. So this approach is just an alternative approach to compensate for this lack of data.
Thank you. I actually have a quick follow-up question.
Yes,
do you think it's possible actually to obtain more training data by actually taking some existing projects and reverse engineering models that you could train models with?
I actually, before doing this project, I started by doing reverse engineering in order to have more data. But I had messy data because data coming from code, we have for example, repositories, utilities, and for this project, I'm looking for domain models, real world concepts. So it's so this is the another idea to mitigate this problem.
And the last question, how are you going to call your approach? Is it going to be UML pilot or model pilot?
It's as a start. I am working on UML class diagrams.
All right. If we don't have any questions, I would like to thank the speaker. Thank you very much.